Okay, let's begin. So today we are going to discuss about a bifurcation known as pitchfork bifurcation. Okay. Yeah. So what is the first thing we need to ask is what is the normal form of the pitchfork bifurcation? So we have seen a normal form of other bifurcations. Similarly, what is the normal form of this pitchfork bifurcation? Okay. So it's given in this in the following manner: x dot, which is equal to rx minus x cube. Okay, so this is the normal form of pitchfork bifurcation. Okay, so in order to understand what's how the bifurcation is going to happen, let's plot this one, and here the r is our control parameter, and let's tune this r value and let's see what sort of behavioral change the system is going to have. Okay, so let's plot this. So this is the equation, and in this equation say my r value is negative. If my r value is negative, then I am having one fixed point which is exactly at 0. Okay, and what if I increase the r value? So if I increase the r value, then okay, still one fixed point. Okay, when I reach r is equal to 0, no, still one fixed point, right? But if I increase the r value further, what's happening is, see, suddenly we are having three fixed points: this one, and this one. Okay, we are having three fixed points, and yeah, so among these, okay, first when r is negative, we have a fixed point, and that fixed point is the slope is negative, so the fixed point is a stable fixed point. Okay, and when r is positive, we have three fixed points, where this fixed point now becomes unstable fixed point, where these two fixed points are stable fixed point. So what's happening in this bifurcation? When r value crosses the 0, the bifurcation happens such that there was a stable fixed point when r is equal to 0, and that suddenly becomes unstable, and at the same time two new fixed point emerge which are stable fixed points. Okay, so this bifurcation is known as pitchfork bifurcation. Okay, now let's identify what are those fixed points. So this is our system's normal form, and the calculation of fixed points. So x dot is equal to 0, which gives me rx minus x cube equal to 0. So that results in r minus x square into x is equal to 0. Okay, so finally I'll get the x star value where 1 is 0. Okay, so irrespective of whatever the r value, this is always going to be a fixed point. Okay, that we have observed in the graph as well. And another solution is x star is equal to plus or minus root r. Okay, so that's another fixed point, and this fixed point is valid only when r is a positive value. If r is negative value, there is no solution. So that therefore we have one solution which is this when r is negative, and 3 solutions when r is positive. One is this, and other 2 things are this. Okay, fine. So we identified what character the pitchfork bifurcation is having, and what are its fixed points. Now let's do the thing called bifurcation diagram, which is a plot r versus x star otherwise. Yeah. So how are we going to obtain? Just plotting this one and this one, okay, in this graph. So let's plot this. Okay, if I plot, what do I get? So one is this line, which is x star is equal to 0. Another one is this line, which is x star square is equal to r, x star is equal to plus or minus root r. Okay, so this is the bifurcation diagram for pitchfork bifurcation. And in this curves, I also need to mention which is stable and which is unstable. Okay, so we have observed when the solution, there was always a solution when x star is equal to 0, right? X equal to 0 is always a fixed point, and that fixed point was initially stable, and when I increase the value to the positive of r, then that solution becomes unstable. Therefore, this is a stable branch and this is an unstable branch. So I have to put this as a dashed line. Okay. How about these 2 things? These 2 things will be stable. Okay. So we can't have 2 stable next to each other. Okay. So therefore, if this is unstable, these 2 things has to be stable. Okay. So if we do all those things, the bifurcation diagram will look as follows. Yeah, so this is the bifurcation diagram for pitchfork bifurcation. The reason it's been called pitchfork bifurcation is because of the picture which you are seeing now. So this bifurcation diagram looks like a fork. Okay, so maybe that's the reason it's been called pitchfork bifurcation. Okay. Okay, so in this pitchfork bifurcation, this particular normal form is known as supercritical pitchfork bifurcation. So this is called supercritical. Okay, so which means there is something called subcritical. Okay, and what is that subcritical? It has this particular form when x dot is equal to x plus x cube. Okay, so this is a subcritical pitchfork bifurcation. Okay, so what are the solutions for this one? So the solutions are rx plus x cube is equal to 0, and the result is x into r plus x square is equal to 0. So one solution is x star is 0, another solution is plus or minus root minus r. So here if you see we will have 3 fixed points when r is negative, and if r is positive we will have only 1 fixed point. Okay, let's plot this one. Let's see the phase portrait of this one. So this is my supercritical pitchfork bifurcation, and the subcritical pitchfork bifurcation, if I put instead of minus, if I put plus, I'll get this value. Okay, and now if I take this to negative, I am having 3 fixed points. So this one, and this one. Okay, and the thing is, if when r is positive, okay, what sort of bifurcation is that? So that bifurcation is, what sort of fixed point is that? So slope is positive, so the fixed point is unstable. Okay, so when r is positive there is only one fixed point, but that fixed point is an unstable fixed point, and when r becomes negative, okay, so this fixed point becomes a stable fixed point where these two fixed points are unstable fixed point. Okay, for this thing, how the bifurcation diagram looks like. So the bifurcation diagram looks like the following. Instead of this we will be having, yes, so this is how the bifurcation diagram looks like. But in this bifurcation diagram, if you ask which is stable and which is unstable, we have observed that when r is positive, which means this branch, that was an unstable, right? So this will be unstable, which we have to represent it as a dashed line. Okay, and this is stable, so solid line. So next to solid line we will be having an unstable branch. So this thing is unstable, this thing is unstable, and this thing is unstable. So except this one, everything is unstable. Okay, only this one is stable. So that's how the subcritical pitchfork bifurcation diagram looks like. Okay, so if I show it in the book, so this is the picture. Okay, so only this is stable, all other branches are unstable. Okay, now what we are going to do is we are going to see an example for supercritical pitchfork bifurcation. So the example which we are going to consider is this: x dot is equal to minus x plus beta into tan hyperbolic of x. Okay, so this is the system, and for this system we need to verify whether this system is having a pitchfork bifurcation or not. Okay, so let's see. Let's plot this one. So y is equal to minus x plus some constant, let's call that as r, so into tan r into tan hyperbolic of x. So now for this is the r value. Okay, and now Okay, even if okay, so somewhere the bifurcation happens. Okay, see, right now this is having only one fixed point, which is at 0, and now if I increase the value above, I don't know, above, seems like 1. Okay, when R value is above 1, we are having 3 fixed points. Okay, whether it's a supercritical pitchfork bifurcation or subcritical pitchfork bifurcation. Okay, that we could verify by checking the stability of this fixed point. Okay, by checking the stability of this fixed point at x equal to 0. So when R is above 1, when we have 3 fixed point, the center fixed point is a unstable fixed point. Okay, and when I decrease the R value to less than 1, I'm having a fixed point which is a stable fixed point. Okay, so it seems like it's a supercritical pitchfork bifurcation. You could verify what is the bifurcation diagram for supercritical pitchfork, and then you could verify for this system as well. Okay, this is an example for supercritical pitchfork bifurcation, but this doesn't look like the normal form of the pitchfork bifurcation. The normal form of supercritical pitchfork bifurcation is this one. So this doesn't look like this, but what you could do is you could verify this by expanding this tan hyperbolic into a polynomial function and chop out the higher order terms and verify whether we are having this normal form. Okay, and also I want you to verify that critical R value for this system is R is equal to 1. Okay, I leave that as an exercise. Okay, but if we see it in a different manner, okay, we could see that the critical value of R is equal to 1. Okay, how am I going to do that? I am going to do that by plotting the following. By plotting these equations, I am going to consider one function, let's say g1 of x, which is equal to just x. Okay, and g2 of x, which is equal to beta tan hyperbolic of x. Okay, so when these two things are same, then that point is fixed point at x is equal to x star, then g1 of x is equal to g2 of x. Okay, so whenever these two functions intersect and those points are fixed points. Okay, let's plot these two things and let's see when they are going to intersect. Okay, so one is y is equal to x, so that's one line. Another one is y is equal to, here we are using r in the place of beta tan hyperbolic of x. Okay, so here if we see these two lines are getting intersected only at this point. Okay, now let me change the r value. If I keep on changing the r value to above 1, then there is an intersection, right? There is an intersection. See, here, here and here. So those are the fixed points. for this particular R value, this is the X star. Okay, so now how can I verify that when R is 1, the bifurcation happens? We have already seen in our previous video. So the bifurcation happens when there is a common slope at the fixed point, at that intersecting point, right? So which means let's say if its intersection is happening when R is equal to 1, then the slope of this line as well as the slope of this line will be same at this particular point, right? Let's impose that condition. So which means at R is equal to RC, then G1 of X prime is equal to G2 of X prime. Okay, so if I impose this condition, what do I get? So 1 is equal to beta, and what is the tan hyperbolic of this one? Okay, I'm not gonna put this one. Maybe you could put, you will get something. Okay, and if you solve for that one, you will get to know that beta is equal to 1. That's the beta critical. Okay, I didn't prepare it priori, so just write the differentiation of this tan hyperbolic over here and equate that to 1. Okay, and we know that the bifurcation happens when X star is equal to 0. Okay, in the place of X you just put 0, so that you will get to know what is beta, and beta will be equal to 1. Okay, so that's how you could identify what is the critical value. Okay, and also I will leave what is the bifurcation diagram, okay, for this system, so that you will be able to verify whether it's a supercritical pitchfork bifurcation or subcritical pitchfork bifurcation. Yeah, okay, so that's all about the pitchfork bifurcation. We'll see some examples in the next video. Thank you.